Hi folks, my name's Hayley LeBlanc, and I'll be talking today about our work on verifying crash consistency and corruption detection in storage systems. This work was motivated by interest from some of our collaborators and co-authors in Azure Storage into looking at building a formally verified persistent memory key value store for use in one of their internal systems where robustness and correctness are really important. This is challenging. Verification is difficult, and persistent memory introduces some really interesting new challenges when it comes to system design. If you're not familiar with persistent memory, it's a type of low latency and byte addressable storage that was available for a while as part of Intel's Optane project. And while that project has since been discontinued, a similar type of hardware is available in the form of battery-backed DRAM, which is the use case that we're targeting here. There has not been any prior work on formally verified persistent memory storage systems, so the systems we've built here are the first of their kind. Persistent memory is really interesting when we're looking at the robustness of storage systems because properties like crash consistency and corruption detection are really hard to achieve. One of the reasons for this is that persistent memory has a very small atomic write size of only 8 bytes, which means that a lot of standard crash consistency mechanisms are not going to work well with it. There's also a really interesting interaction between crashes and corruption that we're going to keep looking at over the next 15 minutes or so in a lot of detail. So our first goal for this project was to develop new techniques that we could use not only to verify the persistent memory storage system that we wanted to build, but that would be more broadly applicable, both for verified and unverified systems for a variety of types of storage. The other thing that we had to do was figure out what tools we were going to use to build this system. So one of the big constraints for our use case was that we wanted to ensure our system could be integrated with an unverified Rust codebase. And so we chose to use Verus, which you may have heard about at a recent systems conference. It's a Rust verification tool that is designed for low-level systems verification and has really fast verification times. This makes it a lot easier to develop systems and maintain them and have a nice feedback loop there. If we compare Verus to the proof assistants that have been used to build the most similar prior work on verified storage systems, it looks pretty good along these 3 axes. But where it doesn't compare so well is when it comes to built-in support for reasoning about crash safety. These other tools have this support or can easily be made to have it, but Verus does not have any kind of built-in crash safety reasoning, and there are no plans to add it. And so our second goal for this work was to figure out how to verify this property without needing any kind of built-in language support. This is what we mean by tool-agnostic in the title of the talk. And a tool-agnostic technique would have a lot of significant benefits. It would be compatible with nearly all current verification tools, so developers that wanted to build a crash-consistent and verified storage system would be able to choose the tool that's best suited to their system, rather than one of the ones that has this set of features that prior work has required. It also means that as new verification tools come out and improve on the state of the art, we can continue to use these techniques and take advantage of these powerful new tools. So in this talk, I'll be discussing several of the contributions of our paper. We've built the first formally verified persistent memory key value storage systems. One of them is a key value store called CapybaraKV that's built in Verus for the Azure Storage use case. And the second is a toy system called CapybaraNS written in Dafny to demonstrate that our techniques are indeed tool agnostic. CapybaraKV is a pretty large and full-featured system, but it verifies very quickly in under 1 minute. And it achieves performance that's competitive with unverified PM key value stores. So we didn't have to sacrifice performance to get good correctness guarantees here. In this talk, I'll be discussing 2 of the main techniques that we contribute. The first is PoWER, our new technique for crash consistency verification in nearly any verification tool, and a new primitive that we call the corruption detecting Boolean, which makes it easy to atomically update checksums on persistent memory in a way that is crash safe. All of our code is available open source on GitHub. So let's set up the problem that we wanted to solve here in a little bit more detail. Along with functional correctness, proving that our systems work the way that we want them to, we also wanted to ensure that we proved that our systems were crash consistent and could detect data corruption. There are many well-known crash consistency mechanisms that I'm sure are very familiar to many of the folks in this audience. And if we look at corruption detection, a common technique is using a type of checksum called a cyclic redundancy check, or a CRC. One of the big challenges that we found is that handling CRCs interacts with crashes and crash safety in a very interesting way. So we're going to be using this problem as a running example for the rest of the talk. Whenever we want to store data with a CRC, both of those need to be stored somewhere together on our storage device. And when we update them, or when we update that data, we need to update the CRC along with it. This data might be an inode in a file system, or the header for a log structure, or maybe the key or value in a key value store. And depending on the storage device that we're using and how we implement this operation, there are multiple possible states the system could end up in the event of a crash that interrupts this update. We could end up in a nice consistent state where the CRC matches the data, but we could also perhaps lose the new CRC and end up with a mismatch between the data and the CRC there. And there are a couple of different ways that this could happen. For now, let's suppose that we can update the data atomically with respect to crashes, but we're going to relax that soon. Like I said, 2 of these states are consistent. The CRC matches the data, but 2 of them aren't. And if we try to read this data and check the CRCs, we will incorrectly get a report that corruption has occurred. And so this is a situation that we want to avoid. So with this example in mind, let's now really start talking about how we ensure crash consistency. This work was heavily inspired by prior work on testing storage systems for crash consistency. So most of these tools work by constructing a set of possible crash states and then checking each of those states to see if they are consistent. And while this has proven to be very effective, it is unfortunately incomplete. These tools cannot check all possible workloads, and it's generally intractable to check every single crash state for the workloads that we do look at. Verification is a really exciting alternative because it allows us to ensure that every single crash state the system could end up in is consistent, and to prove this before we ever run the code. So it's really desirable for these critical properties like crash consistency. The most common technique for verifying code is something called preconditions and postconditions, and these are supported by the vast majority of verification tools that are in use today. So to see what this looks like, let's suppose we have a function. Here I have a pseudocode function in Verus that goes back to our example and updates some data structure and its CRC. We're going to annotate this function with a precondition, which must be true when the function is called, and a postcondition that must be true when the function returns. In this case, maybe we might specify that the CRC we're storing must actually be the CRC of our data. And when we call the function, and we want to ensure that by the time it completes, we've actually stored these bytes. We could write a naive implementation that simply issues writes with these bytes to storage without trying to do any trying to use any crash consistency mechanism. But we run into a problem here, because as we just saw, there are some potentially inconsistent crash states that we want to avoid. But as I've written our code here, it looks like it should verify. We are satisfying the postcondition when the precondition, and the precondition should hold as well. And so we need to figure out how we're going to reason about these intermediate crash states that could occur if the function is interrupted, and ensure that developers prove they're all consistent. The most similar prior work, a file system called FSCQ, introduced a third type of condition called a crash condition. The idea here is that crash conditions describe the state of the system in the event of a crash. And then the verifier will check that this always holds using a special type of custom logic built into the tool. Now, unfortunately, crash conditions are not supported by the vast majority of verification tools, including the ones that we're targeting here, Verus and Dafny, and there are no plans to add them. So we had to figure out how to verify crash consistency without crash conditions, just preconditions and postconditions. To do so, we're going to make a couple of pretty straightforward observations. First, each time we store some data on our durable device, we are introducing a new set of potential crash states the system could end up in. Each of these crash states can be described before the write is invoked, just based on knowledge of the bytes that we're writing and where we're writing them to and what the storage device looks like at the time of the write. This means that developers can prove properties about these crash states before they invoke a write, and we can encode requirements about those states in the preconditions of some key functions in our systems. And again, because this only relies on preconditions, it can be done in nearly any verification tool. So this is the heart of our technique that we call PoWER, which stands for Preconditions on Writes Enforcing Recoverability. In PoWER, whenever we call our write to storage function, we'll need to prove a precondition that states that for all of the new crash states that we are introducing here, each state is consistent after running some kind of recovery function on it. In this case, consistency means that the CRC matches the data that we have on disk. And so the developer will include a proof of this property for each call they make to write to storage. And as long as they can prove that this precondition holds, they've proven that the operation is crash consistent. We do this for every update in the system, and we prove that the system as a whole is crash safe. That was a super quick overview of the technique. Our paper has a lot more technical detail on it, as well as some strategies that we developed for writing these crash consistency proofs, as well as a discussion of several proofs that we wrote that establish that PoWER is sound and does indeed prove crash consistency. We also describe how to build a system that has verified concurrency and uses PoWER for crash consistency. Now, let's go back to our example for a second. We just looked at how we can prove that an implementation of an operation like this is crash consistent, but we do need a crash consistent implementation to do that. And as I mentioned at the beginning of the talk, this can start to get pretty challenging when we're looking at persistent memory. If we take a look at traditional block-based systems first, this hasn't been a big problem because these devices provide atomic block-sized writes, usually 512 bytes or 4 kilobytes. CRCs are usually 4 or 8 bytes, and so it's very easy to store one CRC per block and then update the CRC and all the data in that block atomically with respect to crashes. And this rules out these inconsistent states we were considering earlier. But if we're looking at persistent memory with its tiny 8-byte atomic writes, things get more challenging because not only do we have these consistent states we saw, or inconsistent states we saw earlier, depending on the size of our data structure, there could be many more inconsistent states we have to deal with. And again, this comes from the fact that we are dealing with a very tiny atomic write size. There's only been one system to really look at this problem before. It's a file system called Nova Fortis, and it introduced an algorithm called tick-tock. At a very high level, tick-tock uses CRCs to detect both bit flips that are causing data corruption, as well as inconsistencies caused by crashes. So in Nova Fortis, with their tick-tock implementation, when we attempt to read any of these inconsistent crash states we could end up in, the CRC check will tell us that something went wrong, and then we'll fall back to a replica of that data structure that hopefully has not been corrupted. And this is a reasonable approach, although some of our prior work on testing persistent memory file systems found that it is hard to do in practice, and Nova Fortis had a couple of CRC-related atomicity bugs. And as we dug deeper into this problem and this existing solution, in the context of a verified system, we ran into some more challenges. We wanted to base our system and our model of corruption and the assumptions we make about CRCs on concrete properties that the algorithms that generate these checksums provide. One of these is the fact that CRCs are designed to detect a small bounded number of bit flips. We have a lot more details on exactly how we work that into our proofs in the paper, but the key thing here is that crashes can result in states that are arbitrarily different and may differ by far more than a few bits. And so what this means is CRCs are potentially not going to be as reliable at distinguishing between inconsistent crash states as they are at detecting corruption. Now, it's still very unlikely that CRCs will collide in a way that hides such inconsistencies, but when we're verifying code, we're doing so because we want to ensure that these key properties hold even in the rarest and worst case scenarios. So the rigor of verification led us to need to develop a different technique that would help us avoid this challenge. What we came up with is a pretty simple primitive that we call the corruption detecting Boolean, or CDB. It's a Boolean, but rather than being backed by 0 or 1, it's backed by the CRC of these two values. This lets us store a Boolean value and its checksum in the same 8 bytes and update both pieces of information atomically with respect to crashes. And we found this to be a super useful primitive in the systems that we built. For example, our Capybara systems use the CDB as sort of a validity bit to indicate whether entries in a table are valid, and also as sort of a replacement for a pointer in a copy-on-write approach that allows us to update large data structures and their CRCs atomically. And one thing I want to emphasize about the CDB is that it is a broadly useful primitive. It is not at all limited to just verified systems, but we only developed it because we were building a verified system and really digging into the assumptions that we were making and the existing techniques that we were going to start from. So lastly, before I wrap up, I just want to talk very briefly about our main system, CapybaraKV, that we built. It's designed for this Azure storage use case I described earlier, and it's a persistent memory key value store written in Verus. It supports concurrent and crash atomic operations on fixed size item and list values, so it's pretty full-featured. It's about 25,000 lines of code in total, but it verifies in under 1 minute on most machines. And in fact, it's usually closer to 20 or 30 seconds. I don't have time to discuss our evaluation due to time constraints today, but one of the most exciting things about CapybaraKV, in my opinion, is that we achieve similar or better performance to a variety of unverified persistent memory key value stores on many common benchmarks. So we didn't have to sacrifice performance in order to get these really strong guarantees of correctness and robustness in this system. So to conclude, I want to emphasize some of our key contributions and a couple of the lessons we learned with this project. We've provided or presented the first formally verified persistent memory storage systems, and in doing so, we developed and introduced some useful new techniques for building robust systems, both verified and unverified. We've also learned that, especially when looking at the CDB, crashes and corruption impact data differently, and so when we want to build really robust systems, we should make sure to handle these two events differently. We also saw that the rigor of verification helped us develop a new technique that goes beyond verification in terms of the benefits that it provides. Our code is open source and available on GitHub if you'd like to check it out, and I'm happy to take questions now.